So let's continue our discussion of finding domains and ranges of functions with multiple variables. So here we have our function of x and y is its natural log function right here. So we want to find the domain and range of this graph. So let's review something about what natural log looks like. The natural log of x, you might remember from pre-cal, kind of looks like this, where the y-axis is an asymptote, and we're saying x is greater than 0. So the idea is the same here. The inside here cannot be negative. This must be positive. Can't even be 0. It must be positive. So that's what I'm going to say. To get my domain, I'm just going to say 9 minus x squared minus 9y squared has to be greater than 0. Not equal to, because remember the natural log of 0 does not exist. So if I were to solve this, we would get x squared plus 9y squared is greater than 0. Whoops, is greater than 9, excuse me, messed up there, brought my 9 over, divided by the negatives. And this would give me x squared over 9 plus y squared is greater than 1. So we ask, well, what shape is this? Oh, look at that. This is just an ellipse. So what this is saying, for this function to exist, all the x, y values must be in this plane. Must be in this ellipse right here. Basically says any x, y in this ellipse works. If I go outside of that ellipse, for example, let's say I let x be 7, oh look, I'll get 9 minus 7. It won't work there. So that kind of gives an idea about how this works. We can make this a hyperbola. Like what if I made this a positive 9? Then we would get a hyperbola. Everything else inside that hyperbola, inside the ears of the hyperbola. All right, so let's go ahead and get our range. Okay, so again, I'm thinking, well, what's the smallest this could be? So if I think the smallest and the largest is always what I want to think. What's the smallest something be? What's the largest the value could be? Well, if I look at the smallest, remember, this is natural log. Natural log goes down to negative infinity. So the smallest this is going to be is negative infinity. Well, what's the largest this can be? Now, this is a tricky question. The largest this can be, this is a tough one. You got to think. This cannot be negative. So there are x and y values that can make this negative. So we want to prevent that. So what happens is if I want to find out what the largest this can be, we're going to take a look at, well, where would we stop? Well, that would be basically when x squared and this 9y squared would equal 9. If this sum equaled 9 here, that's going to make this 0. So we say the largest this could be is the natural log of 9. And the reason why is because that 9 minus x squared minus y squared must be less than 9. Again, not equal to, because of it's a natural log, it can't be 0. So this must always be, so this value right here must always be less than 9. Whoops, got my 9 there. There. So that's the largest. So our range would be anything from negative infinity to natural log of 9. Let's try this next one. That's the hardest one. For the next number 7, to get our domain, well, it's our square root. So we already know that the 4 minus x squared plus y squared has to be greater than or equal to 0. And if you notice, this is our hyperbolic paraboloid. So we're going to say, and that's it. That's my domain. There's my domain. If you want to, you can say it's going to be x squared minus y squared is greater than or equal to, less than or equal to 4. And basically we have to be inside of this hyperbola. So if you graph that hyperbola, right, this is going to look something like this. Our distance has to be within, so anything within this hyperbola would work. What's the range? Well, to get the range, again, what's the smallest this can be is 0. And the largest, let's see here. Is going to be infinity. So this is going forever here, right? Is that plus y squared? Even though x squared can make it weird, but that plus y squared is going to make that infinity. So smallest is 0, largest is infinity. So we can say c is greater than or equal to 0 right there. Easy to do. All right, so let's talk about traces again. All right, so traces. Recall, we've been talking about traces a lot lately. A trace is when we fix a value, x, y, or z, into a 3D equation, and we get like a 2D function right there out of it. Basically, we're looking at like a cross section, and that's what we call these. A trace, we call those cross sections. We wind up with the next another equation, again, that represents the cross section on that plane, of that plane. So we want to identify the quadratic surface and answer the following question. So we want to find the trace on this function when x is equal to the square root of 7. So the first thing I want to do is identify this. So to identify this, I get rid of the f of xy. So I would make this z equals the square root of negative x squared minus y squared minus 9. Squaring it, I would get z squared plus x squared plus y squared, and that's going to equal a positive 9. And this is a sphere right here. But be careful, this is a sphere. This, the original, is a hemisphere. Now, why do I know that this is a hemisphere? Right here, a half a sphere is because, remember, this is the top half, because it's positive, of a sphere. We have to square it to get the entire sphere. So that's why function notation is important. This right here, not a function. This is a function because we're only looking at the top half of a sphere. All right, so the next part says find the trace when we let x equals root 7. So let's go ahead and plug that in. So if we do that, we would get z equals, or if you want to do f of root 7y, if you just want to plug that in right there, we would get, this becomes negative 7 minus y squared minus 9. I'm going to keep it in terms of z. Z equals, this becomes, what's that? Oh, I know what happened. This should have been a plus. Let's fix that. Make that a plus. There we go. That'll make everything right. Fan and dandy. There we go. Plus. That has to be a plus right there for this all to work. So, solving this one, now we would get the square root of 2 minus y squared. Again, I apologize for that. Should have been a plus 9 right there. And I just forgot to carry it over. I got to fix that someday in my notes. So we get z equals the square root of 2 minus y squared. And if you notice, this is not a circle, but a semicircle. So this will be at root 2, root 2, root 2. We can even graph that cross section, that trace. And this is a semicircle on the YZ plane. Let's try number 9 here real quick. Find the trace when y equals 4. So again, I want to find out what shape this is. So if I get rid of this, I'm going to get z equals the square root of x squared plus y squared, or z squared equals x squared plus y squared, and I would get z x squared plus y squared minus z squared equal to 0. This is our cone, our elliptical cone right here. Now remember though, this is my cone. This is my hemicone. That sounds kind of weird. This is my hemicone. This is only half of a cone right here, because we don't have to deal with the plus or minus. In function notation, so remember, if you look at a cone, like so, it will not pass the vertical line test, or the z test, I guess we can call it. It won't pass that z test. It's going to cross it twice. But this is only dealing with the top half of our cone. So my cone would look more like this. That would be our shape right here. So the next step is to determine what would the trace look like. So we would find z when we're saying y is 4, so x comma 4, and that becomes the square root of x squared plus 4 squared. So simplifying it, we would get z equals the square root of x squared plus 16. 16. And, oh, this is a weird shape right here. So let's go ahead and simplify this. We would get z squared minus x squared equal to 16. And this is a hyperbola. But it's not a full hyperbola, right? This is a semi-hyperbola. This is our actual answer right here. It's a semi-hyperbola. I just did this part to find out what shape it looks like. So if I were to graph it on the xz plane, it would look kind of just be the part like this. It would look just like this. Like something sticking to arms and legs. Alright, the last note we want to take a look at, we want to write the equation of an elliptic cylinder centered at the origin and opens along the x-axis. So we talk about this is that odd one out, right? That's that odd one out. And it has the vertices 0 plus or minus 2 and 0, 0 plus or minus 3. So this is a cylinder on the because this is my odd one out, this is going to be a cylinder on the YZ plane. So if it's a cylinder, it's elliptical, so I'm going to draw an ellipse. Ready? On the YZ plane, y squared over a squared plus z squared over b squared has to equal 1. Now, remember, this is talking about my y's. This is talking about my z's right there. So if I were to kind of look at this, we're only on the YZ plane. On my y's, we're going out 2 units. And my z's, we're going out 3 units. So I could graph this. This is just what you did 2 years ago in pre-calc. We're saying that in my y's, so my a here is going to be 2, my b is going to be 3. So therefore we would get y squared over 4 plus z squared over 9 equal to 1. Alright, hope you guys enjoyed this lesson. Please like and smash that like button. Ring that bell for more news. Alright, I'll see you guys later. Bye-bye.